Hi, I'm Amanda Olson, and this is part 2 of the calculus discussion of continuity video. So we're going to just go straight to example C. For example C, this function h of x, I have went ahead and entered this piecewise function graph into Desmos. You don't have to use Desmos. You can use whatever you want to graph it. Use a pen and paper if that's all you have. But I've graphed it. And we're going to just kind of consider this graph and discuss this continuity. So when I discuss this continuity, I kind of look at some things. We kind of want to zoom in on where it's interesting. Now, definitely calculus wise, I can, draw the entire graph without lifting my pencil. The only place where I'd have to lift my pencil is where I'm dealing with specifically x equaling 0. But these actually, have the same limit when x equals 0. So if I just consider this first part, it's defined when x equals 0, and when x equals 0, my function output is 1. So that works nicely. And then when I graph this other piece, I still see that as x equals 0, my output is 1, even though the function's not defined there. So what we have is we have the first criteria for continuity is met. The function's defined when x equals 0, it's defined to be 1. We have the limit from the left side as x approaches 0, from the left is 1. The limit as x approaches 0 from the right side is 1. So the limit as x approaches 0 is 1. So that's second criteria for continuity. The limit does exist. And then the third criteria, we can see that the function value and the limit value both agree. So for this function in particular, it is continuous across the domain, even though it kind of has like a silly shape. The last function we'll look at is this sine of x graph. So we consider the sine of x. And for this graph, it's continuous on its entire domain. I can zoom out, and there's no place where there's any breaks. There's no place where I can't, draw the graph without lifting my pencil, that sort of definition. And looking at it, for every point on the graph, it's defined over the reals, the sine function is. So that first criteria for continuity is met. The second criteria for continuity, the limit exists and it equals exactly what you'd expect. And then that third criteria, all of the limits and the function values are agreeing. We don't have any kind of like outlier points or anything like that. So this is continuous across the reals. So then moving on, we will talk about one-sided limits and continuity on a closed interval. So we've already looked at continuity from the right side and the continuity, or excuse me, we've looked at limits from the left and limits from the left and limits from the right. We've already discussed one-sided limits. We just want to expand that. So when we take into consideration a function that maybe isn't defined over the reals, we can still talk about continuity. Because if you have a function, and a common example might just be like the square root of x. And I'll give a very rough sketch of that graph. If I have a function like y equals the square root of x. Okay, well, I'd have to lift my pencil someplace in order to draw, kind of that stopping point, right? And so we have a spot where my graph is actually not defined. And erase some of this. So we have a spot where our graph is actually not defined, and we have infinitely many spots where our graph is not defined. the limit, because at x equals 0, because that limit from the left side is actually not defined. We don't have a left-sided limit. Because of that, we can't discuss the limit at x equals 0 because we only have a right-sided limit. We don't have a left-sided limit. So all of a sudden, you know, we have the second criteria for continuity is not met. We don't have that limit existing because it doesn't exist at x equals 0, because we have that we don't have any values to the left of 0 for our graph. So in order to make it so we can talk about it being continuous at the specific point, x equals 0, we add another theorem for continuity. And so if we have a function that, you know, we consider the limit on the left and the limit on the right, when we look at those, we can talk about continuity on a closed interval. And we can say that a function is going to be continuous at those boundary or those border points. If it's a left boundary point, then we only need the right side limit to exist. So in other words, you know, with this kind of expanded definition, my function is going to be continuous at this boundary point when x equals a, and at this boundary point when x equals b. And that's because this amendment to our previous theorem says, okay, if the right-sided limit exists at that left boundary point, then the function's continuous, provided, you know, the limits agree with the function values, and similarly for the right-sided limits. And all of a sudden we can talk about functions being continuous when maybe you don't have the limit exist completely. And so that just works really nicely for things like radical functions, where we saw, for example, the square root of x, where our function's not defined when x equals 0. This just gives us something else to work with. Further, some other properties of continuity we have is that the limit of a composite function, limits hold under composite functions. And so we can talk about continuity holding in similar ways that function limits hold. So we have scalar multiple holds under continuity, sum and difference hold under continuity, products hold under continuity, and quotients hold under continuity, provided that g of c doesn't equal 0. So that kind of gives us some nice things to work with. So hopefully this gives you a little bit of an understanding of continuity, and you can use that to then work some examples for continuity problems. Thank you.